Hello everyone, my name is Anurag Raj and I have pursued my BTech from IIT Roorkee. I have been teaching since 2016 and it has been 8 years in my teaching career. I have produced multiple All India ranks and the topic that we'll be dealing today is a very common topic that many students has confusion in the minus I effects of following groups. The groups that we'll deal today is N plus, let's say, ethyl, N plus, and 3 methyl group are there. NH3 plus and N plus CH3 H H and then N plus CH3 CH3 CH3. So if I tell you to arrange this group in the order of their minus I effect, decreasing order of their minus I effect. So most of the students, the first thought that comes to most in mind of most of the student is what they do is, like, let's say these two group we are taking and we are trying to arrange them. So CH3 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 and NH3. Now if we compare these two group, most of the students what they do is they think that the CH3 being an electron donating group, it will donate electron and 3CH3 will donate a lot of electron. So this positive charge on this nitrogen will go down and the electron withdrawing character of NCH3 will be less than NH3 plus, which is totally wrong. And why it is wrong, that only we'll try to understand over here so that we can grasp the concept in a much better way and so that we cannot never forget what we have studied. Now what was wrong over here and what is the actual reason behind uh, and what is the actual order over here. So now let's compare let's take a simple group and let's try to compare them. Suppose we are taking this 3R attached with this nitrogen and 3 hydrogens attached with this nitrogen. Now what is happening over here is, actually you see this R group being it is a large group, and since it is a large group there will be a repulsion between them, and due to this repulsion, this is a van der Waals repulsion, and now you see this R group will have certain number of hydrogens, moving hydrogen in them, so their van der Waals radius, van der Waals sphere will be large, and because of this large van der Waals sphere of this R group, they will experience a repulsion between them. Now if I talk same thing about hydrogen, hydrogen is just a very small group, so the van der Waals sphere of hydrogen is really very small, and so there will be negligible repulsion in this case, but the repulsion over here in the first case Nr3 plus will be really high, and because of this repulsion what will happen, these groups will try to move apart, and in turn this bond angle between R and R will increase. So I can say that since van der Waals repulsion is increasing, the spacing between the groups is increasing, and which in turn is increasing the bond angle between them. Now if I try to understand what is the effect of this bond angle, increase of bond angle on the stability or on the minus I effect of this particular group, I have to delve down into the concept of chemical bonding. And now you see, in chemical bonding we have read a certain things. Let's understand those things with example. Suppose if I am taking three compounds just to understand: carbon triple bond, carbon hydrogen, CH2 double bond, CH2, and CH3 single bond, CH3. Now the hybridization in the first compound will be sp, the second carbon will be sp2, and carbon in the third case will be sp3. Now if I talk about the S character, percent S character in the first case will be 50%, percent S character, and in the second case it will be 33.33%, and in the third case it will be 25%. And if I talk about the bond angle, the bond angle will be 180 in the first case, 180 degree, 120 degree in the second case, and 109.19 degree 28 minutes in the third case. So now a very common observation I can take out from this table, that as the S character is increasing, the bond angle is also increasing. So I can say from here that percent S character is directly proportional to bond angle theta. Now I also know from the concepts of chemical bonding that percent S character is directly proportional to electronegativity. So percent S character is directly proportional to electronegativity. So combining these two, I can say that theta is directly proportional to electronegativity. Now this is the concept that we require and will be using over here. So now once again I am moving you through what I have done from the chemical bonding itself. I have taken three examples. In the first case, the compound is having sp hybridization in carbon atom. In the second case, it is having sp2 hybridization. In the third case, it is having sp3 hybridization. So now when the hybridization is sp, the percent S character is 50%. In the second case it is 33.33%, and in the third case it is 25%, and the bond angle corresponding to that is given over there. Looking at the table, I can confer out that percent S character, as it is increasing, the bond angle is also increasing. So I can say percent S character is directly proportional to bond angle. And the third case, and one more thing that I know from chemical bonding is that percent S character is directly proportional to electronegativity of the central atom. So combining these two, I can say that bond angle is directly proportional to electronegativity of the central atom. Now if I bring back this conclusion which I have derived out from chemical bonding over here, I can say that theta is directly proportional to electronegativity. So when theta is increasing, electronegativity is also increasing. Now you see, I can certainly say that this nitrogen over here is more electronegative as compared to this nitrogen over here. Now this concept we already know. Now this is a very important concept. You see, I can certainly say that the electronegativity of central atom is not always constant. It depends upon the surrounding atoms. If we change the surrounding atom, the electronegativity also changes. Like in case of PCl3, the electronegativity of phosphorus is not equal to the electronegativity of phosphorus in PCl5, or I can say the electronegativity of phosphorus in PCl5 is not equal to the electronegativity of phosphorus in PF2Cl3, because the surrounding atoms are changing, and I can certainly say from this concept that the electronegativity of the central atom will also change. Now, what is happening because of this over here? Now you see this nitrogen being more electronegative, and the positive charge on this nitrogen will decrease the stability of this nitrogen. Now we all know one thing, that positive charge on an electronegative atom, more electronegative atom, makes it unstable. Now in some book this nitrogen is also referred as panicking nitrogen. Panic nitrogen. This nitrogen is in state of panic because it is more electronegative, and it is having a positive charge. So what it will try to do, it will try to attract more and more electron toward itself to decrease its positive charge. So now you see, earlier what we felt that Nr3 was, by common observation, what we felt that Nr3 would have been less electron withdrawing as compared to NH3. Now through the concept I can certainly say that Nr3 plus is more electron withdrawing as compared to NH3 plus. Now one more observation I would like you to understand over here, that as the value of R increases, or as R becomes more bulkier, the value of van der Waals repulsion will also increase, and in turn this electron withdrawing nature will also increase. So combining these factors, I can certainly say that when ethyl group is attached, and when methyl group is attached, this ethyl one will have more electron withdrawing nature than methyl one. If it would have been propyl attached, then propyl would have been the largest one. So now among these examples I can say A will have greater electron withdrawing nature as compared to B. Now among these three, if I compare, now you see there is no repulsion, concept of repulsion over here in NH3, and over here in these two compounds also, if I assume also that this sphere or van der Waals sphere of this CS3 is much greater, then also hydrogen are very small, and the repulsion, steric repulsion between the van der Waals sphere of CS3 and hydrogen will be negligible. So I will not apply the concept I have applied over here. Now why am I not applying over here? Because here the repulsion was greater, so the molecule has to move apart. Now these are hydrogen, the repulsion won't be there, so because of which the factors that were working over here won't work over here. So now what is the factor then that will work over here? Simple electron donating nature of CS3. Now since CS3 is electron donating has electron donating nature, the positive charge over here will decrease. Now in the third case also, you see CS3 is written side by side, but if I arrange these three groups, now suppose this one is nitrogen and these are two bulky CS3 group. So what will happen, this CS3 will move like this and nitrogen will come in between, and since these two CS3 groups are far apart, they will not face repulsion, or their van der Waals sphere will not be close so that the repulsion would happen. So in the third case also there will be no repulsion, and what we will judge over here, from which factor we will judge over here, is electron donating nature plus I effect of CS3 or plus H effect of CS3. Now combining all the factors, I can say that A is greater than B, and then will come after C, and then after D, and then after E. Now there are few points after this you should keep in mind. First, where you will apply this concept that repulsion will happen whenever the three groups are alkyl groups, all of the three must be alkyl group. If any one of them becomes hydrogen, the repulsion factor won't be there. So if all the three groups are there, we will apply this factor that as R increases, the electron withdrawing nature also, the bulkier the R is, the electron withdrawing nature is more. Now if any one of them is hydrogen, we will see the electron donating nature. So combining all three, we will get this concept. So that would be all for today. Thank you so much.